So our goal now is to define the determinant of a matrix in such a way that the determinant of an operator coincides with the determinant of that operator's matrix. And we'll see this is independent of basis by the way that we set it up. And that's one of the big things that makes determinants important or useful, despite what our author might say. So for this, we need the idea of a permutation. So a permutation, so we can write it as a sequence, is a rearrangement of the list 1, 2, up to n. So, in other words, it's a bijection from the set 1 up to n to itself. So the set of permutations is permutations of 1 through n, or actually I guess I'll write these as lists because I think that's what Axler does. So that no, I was right before. The set of permutations of 1 through n. So that's the set. A given permutation would be written with round parentheses, but the set of things being permuted is not. So the set of permutations is denoted perm n. There's also other notations for it though. So in particular, since these are bijections, they are invertible. We also have that the identity is a permutation. So this is the identity because it's saying, if you read the fine print here, let me move this over just a little bit. It's saying that M1 is equal to 1, M2 is equal to 2, Mn is equal to n. Or if you want to think of it even more as a permutation, M of 1 is equal to 1, M of n is equal to n. So this is the identity permutation. I will just put that over here somewhere. Okay, and what else do we have? We know that, there we go. Oh, heck. I goofed up an equal sign. There we go. So, and what else do we know? We know that these bijections can be composed and the result of composing two bijections is another bijection. So in other words, the result of composing two permutations is another permutation. And so these all together then tell us that the permutations form a group. And so the first line here, that they're invertible, that one says that if we have some element sigma in, oh, and by the way, these form a group called Sn. That's what it's usually denoted. So when you think of it as a group, we call it Sn, and that's for the symmetric group. Symmetric group on n elements. If sigma is in Sn, then its inverse is in Sn. So it contains its inverses. The identity element is in there. And we also have that if you have sigma and tau in Sn, then the composition of them, so first do sigma, then do tau, that's also in Sn. And so that means that we actually have a binary operation which is closed, in other words, puts you back in the group. So those are the axioms for it being a group. So it turns out it's actually a very well-studied group. It's fundamental for the study of lots of other groups, so on and so forth. There's a whole huge literature about it. So let's see. So when choosing a permutation, so if I'm saying, hey, let's pick an element of Sn. Okay, so what should we choose? Well, what can we put in the first slot? So there's going to be, well, if we've got n elements to choose from, then there's n choices for our first element. So and then after let's see, so we build our group element. So here's our permutation rather. So we say, okay, so what do we put here? Well, there's n possible different things that it could be. Okay, then what do we put in the second slot? Well, we've already used one thing, so now there's only n minus 1 choices left. Oh, I said there. I should have said there are. So then there's n minus 1 choices for what to have as M2. And then there's n minus 2 choices for what to have for the next one, and so on and so forth until you get down to the end, and then there's just 2 choices for that one, and then there's just one thing left, and it's kind of forced on you. And so altogether, how many elements do we have in the permutation, in the set of permutations? There's going to be n times n minus 1 times da 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 da. So n factorial permutations. So that n factorial total possibilities. So let's look at the permutation group on 3 elements. So perm 3. So this looks like, and what do we have? So we can have the identity 1, 2, 3. We can have 2, 3, 1. We can have 3, 1, 2. So those are both what we call cyclic permutations of the identity. In other words, it's just like we took the 1 and moved it to the end of the line, and then we get the next one, and then we took the 2 and we put it at the end of the line, and then that gave us the next one. So we're just sort of cycling them. But then there's other ones that you can't get by cycling. So 3, 2, 1, and whoops, 1, 3, 2, and 2, 1, 3. Okay, and you'll notice actually that you get these ones by cycling them. So if you take 3 and you put it at the end, or actually here, let's do it the other way around. If you take 1 and you put it up at the beginning, then you go to this one. And then if you take 2 and put it up at the beginning, then you get to this one. So let's see. We also have a closely related idea, and this is not technically part of the definition, but I think it helps sort of show what's going on. And it's called a permutation matrix. So a permutation matrix comes from the identity by swapping rows. So if you remember your elementary row operations, you do some row swaps, interchange some rows. And so this means that in a permutation matrix A, AJK is going to equal 0, except row swaps preserve this property of the identity that each row has exactly 1, 1 in it, and each column has exactly 1, 1 in it. So except for 1, number 1 in each row, and 1, number 1 in each column. So some kind of Sudoku type thing. So the idea is that multiplying a vector by a permutation matrix permutes the entries of the vector. So if we, so suppose we've got some x in Rn, and we multiply by some permutation matrix. Actually, here, I'll just call it A. And then we get some permutation of x. So suppose we're in the 3x3 case. So let's see. So if I take the permutation 3, 1, 2, I could write this as a matrix. So 3. So that tells me that I've got a 1 in the third column, and then 1, that tells me I've got my 1 in the first column, and then 2 tells me I've got my 1 in the second column. So there's an example of a permutation matrix corresponding to 3, 1, 2. And then you see if I multiply this against the vector 1, 2, 3, then let's see, when I do the multiplication, this one against this guy is going to pick up the 3. So I'll have my 3 up here. And then when I do this one against this vector, I'm going to pick up the 1. And then with the last one, I pick up the 2. So I get that. And then you see 3, 1, 2, there's my 3, 1, 2, right? So it's setting up a bijection on the set of 1, 2, 3, and this is a way to express it in terms of matrix multiplication.